In this video, we are going to find the probability distribution of the so-called envelope of a Gaussian signal. This kind of probability distribution is also called Rayleigh distribution. And let me also sketch very, let's say, quickly a random signal like this. And you have to think that this is the axis of time, for example, and we are interested in finding the distribution of these positive peaks here, how they are distributed. We are going to call the random variable of the signal I with a tilde here to denote the fact that this is a random signal. I depends on time, and let's also put a subscript here n to denote that this is a noise, Gaussian noise. So the signal will have the following distribution. It will be normal or Gaussian, so Gauss with zero mean, so mu is equal to 0, and the standard deviation is equal to the square root of the variance, which I will call psi 0. This is just notation. And the signal can be written like this, with some kind of Fourier expansion. So we sum over n, this coefficients c sub n, and then here I have the cosine of omega sub nt minus the phase phi n. Now let me cancel this, because otherwise it will get confusing. You have to remember that this signal has a Gaussian distribution with zero mean and standard deviation equal to sigma, which is equal to the square root of psi 0. And let me put a tilde here under the phases, because the phases will be the random variable appearing on the right hand side. So this is a random variable, therefore we should have some random variables here as well on the right hand side. And the frequency, the coefficient c sub n will be scalars, so they are not random variables, whereas phi sub n, all the phases, phi sub n will have a uniform distribution, and they will be uniform between 0 and 2 pi. And now what we are going to do is we are going to rewrite this signal to find the envelope. We will find the envelope of the signal, and then we will find the distribution of the envelope. That's what we want to find. In order to do that, I'm going to rewrite this signal like this. It can also be written as the real part of. Now let me tell you that these coefficients, the frequencies, and the phases are all real numbers. So the phases are random numbers, but they are still numbers, real numbers. And now here, if I take the real part of the sum, and here I have c sub n, and instead of the cosine, I can put the complex exponential e to the I omega nt minus phi sub n. Now, of course, these two are equal, because when I take the real part, I have to consider the real part of this complex exponential, which will give me the cosine. And this, of course, can also be written as the real part of, now I have summation over n, c sub n, cosine of omega nt minus phi sub n, and then here I have plus I summation over n, c sub n, sine of omega nt minus phi sub n, like this. Now, this part here is exactly equal to I sub n, and I'm going to call it also I sub c, where c stands for cosine, because this first part contains the cosines, whereas the second part here, the imaginary part, contains the sines. So I'm going to rewrite it as is, I sub s. And from I sub c and I sub s, I can obtain the envelope. And in particular, I can write a random variable r equal to the square root of I tilde sub c squared plus I tilde sub s squared. And now I'm going to motivate this a little bit more rigorously. So this will be the envelope. we want to find the distribution of this random variable r, which depends on time, because we know that I sub c and I sub s both depend on time, and you can see that from here. And they are random variables because they contain phi sub n, so both of them contain phi sub n. And we know that this signal is Gaussian, and if we replace the cosine with the sign, we're not going to change the distribution. So I sub s will also be Gaussian with the same mean and the same variance, or standard deviation. So the standard deviation will be the square root of the variance. And now let's do one step at a time. So let's not rush things. And now I want to show you why R is the envelope. In particular, we can rewrite our signal I sub n in this form. I can write it as R. Remember, this is a function of time, and it's this R here, times the cosine of another random variable lambda of t. And now the cosine of lambda of t is defined to be I tilde sub c over R, which is a random variable. And the sine of lambda of t is equal to I sub s divided by R. Now, if you take the cosine and you square it of lambda of t plus the sine squared of lambda of t, you can easily check that you're going to get 1, right? Because we know that we defined R like this, and we can also see that the cosine, the absolute value of the cosine will be less than 1, less than or equal to 1. And similarly, the absolute value of the sine. So it means that these are properly defined because, of course, the cosine and the sine of an angle should be between -1 and 1, right? And we have also proved that this trigonometric identity holds, and this is important. So we can define an angle lambda of t such that the cosine and the sine comply with these two relations. And then I sub n can be expressed in this form, like this, right? It will be some kind of sinusoid with this amplitude, which depends on time. And that's why now I can understand why this will be the envelope, right? Because I can express my signal like this. So it makes sense to think that this will be some kind of envelope of our signal. Now, the next step is to show that the variables I sub c and I sub s are independent. This is what we want to show next. This is the next important step. And the way to do that is to show that the expected value of the product between I sub c and I sub s is equal to 0. Now we have to be careful because in general it is not true that if this relation holds, so if the expected value of the product between these two zero mean random variables is equal to 0, this does not imply in general that the variables are independent. But this is the case when the two variables are Gaussian. So in this case, the two variables are Gaussian. And in a previous video, I have shown how to find the joint Gaussian distribution of two dependent variables. So we have a parameter in general, a scalar, which in that case I called lowercase r, which tells us whether the two variables, the two Gaussian variables are correlated or not. If this is equal to 0, then the two variables are not correlated, are not dependent upon each other. For two dependent Gaussian variables, as I said, this parameter r is important. And if this is equal to 0, then the two variables are independent. And if you go and check the definition for r, you can see that it is proportional, linearly proportional to this expected value here. So if this is 0, then also this will be 0, and the two variables will be independent. But this is the case only for Gaussian variables. So that's important, because you can express the joint probability distribution thanks to this, let's say, by means of this parameter r. And so what we need to show in this case is that this expected value is equal to 0. And how can we do that? Now, let's do it here. We have to take the expected value of the product between IC and IS. And this will be some kind of average that I'm going to indicate with these angular brackets. And the average will have to be taken over the phases phi sub n. Now, let's do one step at a time. So here I will have the variable I sub c. So we have to sum over n, c sub n, the cosines, omega sub n t minus phi tilde sub n. And then I have to take the product with, let's say, now let's change the index. So we are going to sum over m. And this is the expression for I sub s. We have c sub m sine omega sub m. Now, do not get confused between m and n. It's quite difficult to hear the difference when I pronounce them because they are quite similar, but you can see that from my handwriting, hopefully. Omega sub m t, and then here I have minus phi tilde sub m, like this. And now I can split the product of these two summations into a sum of two different summations. In particular, a summation where n is equal to m and another summation where n is not equal to m. So let's do it. We have a summation over the index n, for example, and here I have c sub n squared, because as I said, in this case, n is equal to m. And then I have the cosine of omega sub n t minus phi sub n times the sine of omega sub n t minus phi tilde sub n. And then I have plus another summation where the index n is not equal to m, c sub n, c sub m, cosine of omega sub n t minus phi tilde sub n times the sine of omega sub m t minus phi tilde sub m, like this. And now I have to integrate over the phases. In particular, if we consider the average of this, now we have the average, we have to calculate the average of the sum of these two random variables. And if I take this second one here, well, the average of this will be simply equal to 1 over 2 pi, and then I have to integrate from 0 to 2 pi, but I have another integral, 1 over 2 pi, integral from 0 to 2 pi, because I have to integrate over phi n and phi n. I know that they are different, so I have to integrate over phi n and over phi m. And here, inside the integral, I will have to remove the tilde, because when I integrate here, they will be considered just simply as numbers. Okay, so here I will have to rewrite exactly the same thing. The only difference will be that this variable will be written without the tilde, and this variable here will be written without the tilde, but this is just notation. If you want, you can put the tilde here and integrate over this quantity the way it's written. So just like that, you simply have to copy this quantity, this thing, here for the integrand. And you have to integrate that, but it's very trivial. It's very easy to know what the result will be, because if you integrate this cosine from 0 to 2 pi, you will get 0. It's very easy. Similarly for this one. So this will give a 0 contribution. It's very easy to check. And now we have to do something similar for this first summation. In this case, we only have to integrate once, if you think about it, because this variable is equal to this one. So I will have to integrate from 0 to 2 pi and multiply by 1 over 2 pi. And then here I will have this integrand. And in particular, the integral will be performed only over the cosine omega n t minus phi n times the sine omega n t minus phi n, and I have to integrate over phi n. And still, this is quite an easy integral. If you integrate this trigonometric function, you're still going to get 0. So it's very trivial. And therefore, we have proved that IC and IS are independent. And it means that if I consider the probability density function, the joint probability, FIC, IS, which depends on the variables x and y, this will be equal to FIC of x times FIS of y. So it is simply given by the product of the marginal distributions, which is not the case in general if the two random variables, for example, were correlated or dependent. But in this case, it is very easy. So this marginal distribution will be the Gaussian probability density. So we have 1 over square root of 2 pi psi 0. So this is the variance. And here I have e to the minus x squared divided by twice the variance, so twice psi 0. We know that the variable IC has a 0 mean, so that's why here we only have x. Otherwise, here we would have x minus mu squared. If mu were non-zero, then this is the general distribution. But we know that mu is equal to 0, so we can rewrite it like this. And then here we have 1 over the square root of 2 pi psi 0 e to the minus y squared divided by 2 psi 0. It's very trivial. So all in all, we can rewrite this as 1 over 2 pi psi 0 e to the minus x squared plus y squared divided by 2 psi 0, like this. And now what we are going to do is we are going to polar coordinates. So from the variables IC, IS, we are going to polar coordinates, which means that we are going to go to the variables r and theta. But what is r? So if we go to polar coordinates, r is equal to the square root of IC squared plus IS squared. So if we consider these as random variables, we should put a tilde if we want to be consistent with our notation. Okay, so whenever I don't use a tilde, it means that the random variable has taken a specific value. So if I write r without the tilde, it means that r tilde has, let's say, taken the variable, the value r, or whatever value. So it could be equal to any value from 0 to infinity. And theta is the angle for polar coordinates. So basically it means that IC is equal to r cosine of theta, and IS will be r sine theta, like this. And if we want to find the joint probability density fr theta, which depends on r and theta, so in this case I will write r and theta without the tildes, because these are just the values that the random variables take, this will be equal to f IC IS of r cosine theta, r sine theta. So I have to substitute these variables here, these values. So it means that IC, which takes the value x, will be equal to r cosine theta, and IS, which takes the value y. Remember that we have substituted, here we have substituted y. So it means that IS takes the value y. Y will be equal to r sine theta, like this. And then we have to multiply this by the Jacobian, dxy dr theta. But the Jacobian for a polar transformation is very trivial. It is just equal to capital R in this case. It is the radius, the radial distance, R. And now if we want to find the probability density of R, which is actually what we want to find. It's the probability density of the envelope. This will be a function of R, and we simply have to integrate over theta the distribution f r theta of r theta, right? So we have to integrate that over theta from 0 to 2 pi. And we can use this formula. So this will be equal to r from here, and we have to divide by, if you recall, 2 pi psi 0, and then we have this. So we have 2 pi psi 0. Here we have the integral from 0 to 2 pi. We have the exponential e to the minus x squared plus y squared will become r squared cosine squared theta plus r squared sine squared theta. So we have minus r squared divided by 2 psi 0 d theta, but this will be a constant with respect to theta, so it would be trivial to find the result. We have r divided by psi 0 e to the minus r squared divided by 2 psi 0. And this is actually the result that we wanted to find. This is called the Rayleigh distribution, and this distribution is defined from 0 to infinity because r is non-negative. And this function can be sketched like this. So fr, if we sketch it from 0 to infinity, so this is the axis r, it has a maximum at r equal to the square root of psi 0. So its maximum is located at r equal to the standard deviation of the signal, and then it goes to 0 at r equal to infinity. So if we consider the function f sub r of r times dr, this will be the probability to find the peaks between the value r and r plus a small increment dr. And this probability here is maximum where r is equal to the square root of psi 0. So it means that this function will be maximized when we are in the vicinity of the standard deviation.